Welcome back. In this lecture, we will describe some RNN architectures for different use cases. And that's the main objective for this lecture. Now, the architecture that we showed you is kind of the default, and we talked about this idea of language translation. We showed you this unfolded view where you have a many-to-many relationship. So many inputs give you many outputs. And so this is directly dealing with the language translation use case. That's an obvious example circumstance where you'd want to do that. But you may not always want to have many outputs for the number of inputs. You may want to go from a one-to-many architecture. And this case might be something like image captioning, where you have a single image, but then the output will be multiple words to caption that image. And this is a great example of where you would have a one-to-many kind of architecture. Now, of course, you could also have many-to-one, where you have a lot of text, and maybe you want to just classify that text based on something like sentiment. Or there's companies that want to look at, if a particular product is being discussed in social media, and maybe the product is a brand name that is also a regular, has, a regular standard context that is used. So you don't want to confuse that standard context for the use of the brand. These types of use cases are where a many-to-one RNN architecture would make a lot of sense. So let's talk about a specific type of technique called LSTM, which stands for long short-term memory. And the concept is we want to enhance the inner workings of the recurrent neural cell with a gate. And the idea is that as you go through a sequence of data, so as you listen to things that I talk about in this lecture, for example, there might be certain items that you would need to understand later on, so you'd want to hold on to those. And there are certain others that don't necessarily influence the context of what I'm going to say later, and those can be forgotten. LSTM uses this idea of adding additional layers within the neural units to gate this information in a much more clever way. So, but that aside, this is an enhancement on an RNN. You still have common weights across neural cells. It's just across the recurrent neural cells, you just now have more layers and structure within it. You will have more weights, but the weights within each cell will still be the same. Now, even despite the advances with LSTM, there are still challenges, such as the long-term memory is still quite limited over very long sequences of information, and the relationship between cells prohibits parallelization. So if you recall from an earlier lecture, we showed, what if we did language translation where each word in a sentence had its own neural network like that? Well, that would be terrible for language translation, but it would be great for performance because I can easily parallelize, a separate neural model with multiple processors. That goes away by taking a hidden state and transferring that hidden state from one neural unit to the next, and so on. There's another interesting issue in that if you think back to the lectures on convolutional neural networks, we dealt with images which are really just giant matrices because pixels are just numeric values specifying a color intensity. Language is not like that. So you have to do what's called an encoding of the text. So how do you perform this initial encoding is also another key challenge with RNNs. So anyway, this concludes our lecture on RNN architecture types. Stay tuned for more content.